In this video, we're going to demo using R to do inference on difference of two means. The data come from diamonds. These are 1 carat and 0.99 carat diamonds. And our research question is the average point price of 1 carat diamonds higher than the average point price of 0.99 carat diamonds? Let's start by uploading our data into RStudio. I click on the upload button here, locate my data set in my computer. It's a CSV file, and I import it into RStudio. Once it's here in my files pane, the next step is to import that into my workspace so that it's usable for the remainder of the analysis. Locate my file, hit open, and I want to make sure that heading is selected as yes so that RStudio knows that the first row of the data set is a header row as opposed to actual data. And finally, I click on import. We can take a look at this data set real quick. We can see that there are 53 observations here. Each observation is a diamond for which I have information on its carats. So this is either a 0.99 carat diamond or further down a 1 carat diamond. I have the total price of the diamond as well as the point price. This is simply the total price divided by either 99 for 0.99 carat diamonds, or in the case of a full carat diamond, that's the total price divided by 100. I also have information on other attributes of diamonds. The price of a diamond is determined by its carat as well as its cut, color, clarity, and depth, but we won't be using these variables in this analysis. In order to answer this question, I might want to do a hypothesis test, and for that I want to first start by loading the inference function. And once it's loaded, you'll be able to see that in your workspace. And to use the function, I want to type the name of the function and then give it a bunch of arguments. The first argument is my data. This is the numerical data that I'm testing. Remember, my numerical variable here is the point price, so that's diamonds $point price. And my grouping variable is a categorical variable. I have two types of diamonds here that I want to compare. Some of them have 0.99 carats and the others have 1 carat, so that's the carat variable there. I'm comparing their averages, so my estimate is the mean. I want to do a hypothesis test. In this hypothesis test, I have a null and an alternative hypothesis. The null hypothesis sets the two average point prices equal to each other. In other words, my null value is 0. Since it's a numerical value, I don't need to put that in quotation marks. And my alternative hypothesis is greater than, so I'll just type greater. But I also want to make sure that in the alternative hypothesis, these groups appear in the order that I want them to. So that's 1 carat diamonds greater than 0.99 carat diamonds. So I can specify this order to the function. Since I am going to be giving it two arguments, I list them using the C function. The first group is PT100 for 1 carat diamonds, and the other group is PT99 for 0.99 carat diamonds. And lastly, let's start by doing a hypothesis test using a theoretical approach. Let's go through the output here real quick. My response variable is numerical, that's the point price. My explanatory variable is categorical, that's my grouping variable, the carat. I'm doing a test of difference between two means. Let's take a look at our summary statistics. There are 31 carat diamonds and 23.99 carat diamonds. Since these sample sizes are small, I'm going to be doing a t-test. The average point price of a 1 carat diamond is 53.4. The average point price of a 0.99 carat diamond is $44.5, indicating already that in this observed sample, the average point price of 1 carat diamonds is higher than the others. And I'm also given the standard deviations for the two groups. The observed difference between the means is roughly $8.93. And we can also take a look at the side-by-side box plots here, which also suggests that the average point price for the 1 carat diamonds is slightly higher than the average point price of the 0.99 carat diamonds. And my null hypothesis, I set the two population means equal to each other. In other words, I set their difference equal to 0, and in the alternative hypothesis, I say the difference between the two averages will be greater than 0. And we can see that the groups appear in the order in which we indicated to the function. The standard error is calculated automatically for us, and so is the t-score, calculated as the observed difference minus the null value of 0 divided by the standard error. My degrees of freedom is 22 because that's one less than the smaller of the two sample sizes, and the corresponding p-value comes out to be roughly 1%. We can see in the little sketch here that an average difference of roughly 8.93 is a pretty unusual observation, yielding a pretty small one-tailed p-value. With a small p-value as such, we would reject the null hypothesis and conclude that these data provide convincing evidence that the average point price of 1 carat diamonds is higher than the average point price of 0.99 carat diamonds. We can also use a confidence interval to answer this question. For that, I just need to change my type from HT to CI, and I don't need to specify a null value or an alternative hypothesis since I'm not doing a hypothesis test here. The confidence interval comes out to be between 1.54 to 16.3, and the way I would interpret this is we are 95% confident that the average point price of 1 carat diamonds is $1.54 to $16.3 higher than the average point price of 0.99 carat diamonds. The confidence interval agrees with the hypothesis test from earlier because the interval doesn't include 0. In fact, it lies above 0. I can also do this confidence interval using a simulation method, and for that all I need to change is the method from theoretical to simulation. Remember that using a simulation method for a confidence interval basically means bootstrapping, taking bootstrap samples from both of these groups, calculating a difference and noting that and repeating this many times. The inference function does that for you 10,000 times. It may take a minute to run this, and we can see that the bootstrap interval agrees with the interval from earlier such that it lies above 0. The lower and upper bounds aren't exactly the same as before, but that's expected since this is a simulation-based method. Each time you run this function, let's just run the same thing once again, we should get slightly different values for the lower and upper bounds, but they should be in agreement with each other. Lastly, we can also do a simulation-based hypothesis test, but since we're going back to a hypothesis test, we want to change the type from CI to HT, and we also want to, just like before, make sure that we specify a null value and alternative hypothesis as well. The randomization distribution is simply that bootstrap distribution from earlier shifted such that the center of the distribution is at the null value. We can see that it's at 0 from the histogram over here. And we can see that the observed difference of roughly $8.93 is a pretty unlikely observation, and hence our p-value is pretty small, which would mean that we would reject our null hypothesis. Once I'm done with my analysis, I want to make sure that I incorporate all of this in my report. So I open my RMD file, I insert my title, some information about the data. I want to make sure that I'm reading the data set as well as loading the inference function. And in the inference section of my report, I include results from the theoretical analysis as well as the simulation-based analysis. And I click hit init HTML. And if all is good, I should be able to see all of my results showing up in my report. At this point, all I need to do is to incorporate some text that introduces my data and my research question, some exploratory data analysis, and interpretations of my results, and a brief conclusion. And I'm done with my project. I hope that this video has been helpful for doing inference on difference of two means using R. Thank you for watching.